Hello, good morning. Welcome to the class ECE451, Control Engineering. This video is recorded for the class at this Wednesday, which week? Next week, Wednesday's class. All right. First of all, for me, I'm better enough to record the class here right now, and if nothing wrong. Hopefully, I believe there won't be anything wrong. I can go back to the campus on the Friday. Of course, I will send you an announcement to let all of you know. Yeah, I will go back. Tomorrow I will go to see the doctor and follow the instruction. Yeah, I think it will be fine. So far, I'm better. Yeah, the recovery from the surgery now is better and better. Yeah. Okay. Today is for the midterm. Let's go over the midterm exam problems. Monday you took the midterm 2, right? Midterm 2, and now we just go over the problems. I have the solution here. Sorry. Yeah. Okay, this is the first problem. We consider a unit feedback system, and this is the structure, and we know what is a G, and we want to find the type of the system for reference tracking and the corresponding steady state error. Right. So this is a problem related with the type of the tracking. We also need to find the steady state error. So we need to find two things. One is the type, one is the steady state error. So to solve it, we have two different methods. The first method is quite simple. You just follow some formulas, then you can have the result. Here you look at the G. We have one factor S in the denominator. Right? It is S to the 1. The power is 1. It's the first order. Right? S. The other two factors, in denominator we have another s plus 3, and the numerator we have s plus 2. So for that s, we only have that s. Then we know the type of the whole system is 1. It is s to 1, right? The power is 1. If this is like s squared, then the type will be 2. If this is s cubed, the type will be 3, right? Now it's just s, so the type is 1. Then what is the constant k? Actually, this k here should be kv, right? Should be kv, the velocity. This is just s times g of s. And the type is 1. Here's 1. So here is just s to the power 1 times g, and let s tend to be 0. You just multiply s on g. Multiply s on g, you will have s plus 2 over s plus 3, right? That s is cancelled. This s is cancelled. Then the result is s tend to be 0, so you only have 2 over 3. Okay. Now what is steady state error? There will be 1 over k. It is 3 over 2. So we have the result. Yeah, this is just you follow the formulas. Follow the formulas. But if you're working this way, sometimes you do not know what are you doing, right? You find these two numbers, but what are the meaning of them? It's not so clearly. So this is second method. Second method is based on the definition of the tracking problem. Okay. So we find the overall transfer function t, which is g over 1 plus g, right? You use the gain formula. You can find the transfer function of the whole overall system. We have one forward pass with gain g, so g is the numerator. And we have one loop. The loop gain is negative g. So denominator will be 1 minus negative g. Okay. Then you plug in g, do some calculation, you can have the transfer function t. Okay. Now what is the steady state error? This is just a definition. Steady state error is the reference minus output when t go to infinity. Right? It's a steady state, so t is large enough. So here we Just write t go to infinity, and then use the property of the Laplace transform, right? The final value go to the s tend to be 0, right? The final value for t now tend to the s domain. We can use the value when s tend to 0, right? Here's the t go to infinity. Now here's the s go to 0, and in s domain it is still r minus y, but in s domain, and we need to multiply s in front of it. That is the formula, right? Okay, then plug in what is y. Y is t times r, transfer function times input, and then we move r in front, so we get this one. Finally, you plug in what is the t, and put the s here, then we have this formula. Okay, here we do not know what is r. You use different r, the limit will be different. So we choose r equal to this one for different n. That means we use a list of, we have a list of different signals. We use those signals at r. Then you just plug in r here, right? You plug in what is r of t, then in the s domain capital R of s are these values. Then plug in here, you calculate this limit, you can have the value here, right? ESS are these values. Okay, then what is the type? Type will be in the bound, in a boundary. One side you have infinite, one side you have 0. So this is a type. Okay, type is what? Type is 1. Right? Type is 1. Type is 1, and the steady state arrow is 3/2. Alright, so this is a result similar, right? This is a type 1, and the steady arrow is 3/2. Right? Yeah, the same answer. Okay, so this is the first problem. Okay, now let's look at the problem 2. Problem 2. Here we have a unity feedback system which has an open loop transfer function is g of s. This is g of s. This is the plan, right? This plan, and we need to compute the sensitivity of the closed loop system, right? The closed loop transfer function according to the changes in the parameter t. Here you see we have a parameter t in the transfer function g of s. Alright, yeah, then the solution, the closed loop transfer function, right? First of all, you need to know these, and I use a notation capital M for this transfer function. Actually here you can use any letter, right? M or P, Q or R, whatever. Yeah, this is the closed loop transfer function, the transfer function of the overall system. Then it will be g over 1 plus g, because the system is a unit feedback system, right? Yeah, so you need to make sure you know what is a unit feedback system, right? Like here's a -1, here's a g, right? Things like that. This is the input, this is the output. Right? Yeah, this one. Then we need to calculate the sensitivity. Okay. After you get m of s, you check the sensitivity of m of s regarding parameter t. Then this one, this is just a definition. This is definition. dm over m. This is a percentage change of m of s. Right? dm is a kind of change over m, so percentage change of m. And denominator is a dt over t, that is a percentage on t. Then the rate between them, that is a sensitivity. That makes sense, right? Okay, then we do some algebraic calculation. dm over dt times, okay, this m, we can move in the denominator, and this t is in the denominator of the denominator. So it just move up to the numerator. Okay, Then we do the calculation. The first part is dm over dt. So this is a derivative of m regarding t. And m is a fraction. So we just follow the formula for the derivative of fraction. We take the derivative of the numerator times denominator. This is first term in the numerator, right? And derivative of the numerator, it is s plus 1. No t here, so you take derivative, you get 0. So 0 times the denominator. This is denominator, right? The whole denominator. Right? The whole denominator. And minus s plus 1. This is the numerator. Times the denominator, take the derivative according to t. So you have 2t times s squared plus 2s. Then s plus 2 after the derivative, they are zeros. Okay, so we have this one. And then t is just t, copy it. Then 1 over m. 1 over m, here's m, right? 1 over m, you just flip the numerator and denominator. So we did this part. This is 1 over m, right? 1 over m. Okay, then we need some simplify. This is a 0, and then minus s plus 1 times this 2ts squared plus 2s. And here's a t, and here's a t. And this term can be cancelled with this square. Oh, I forgot to talk about this. Take the derivative, you need the square of the whole denominator here, right? Yeah, the formulas look like this. We have u over v, we want the derivative. It will be u take derivative times v minus u times v take derivative over v squared. Right? Things look like this. So I need a square in the denominator. So this is a square. Now this is a just one factor, and here's a square of it. So you can cancel one. So this one was cancelled, and this one you remove the square, right? Just the other one. Then okay, here we can do more simplify. This is s plus 1. Here's another s plus 1, so we can cancel it. Okay, the final answer will be, we have this negative, then we have t here, right? I put the t in the front, and then you see this, I can remove 2s in front of it, right? This 2s, here's another 2s, so 2s times t in the front. After we remove 2s, this term becomes ts, right? ts, and plus 1, right? And denominator is just this, and we also have a negative in front. All right, yeah. So this is problem 2. Okay. Then let's go to problem 3. Third one. Okay. So here we have a feedback system, and we have a g of s, which is suppose g of s looks like this. So it is combined. It contains all the factors like s plus something, right? In numerator is plus 0, and is minus a negative z is 0, and the denominator is a negative p will be the poles. Right? Then here's no more constant, and here I have k. Okay, so this one, and we have rule lockers of the system. We already have the rule lockers. And what are the questions? First one, determine g of s. Second one is determine breakpoint. We have breakpoint. So you can have a look. Determine g of s. We already have a g of s, but this g of s is uncertain. We do not know what are the zeros and what are the poles, and how many zeros, how many poles. Right? We need to determine this thing. And this information you can just check the graph. You can see it. Right? Let me make it large. Okay. Right. So you see, in this graph we have how many poles? These 2 poles, right? And 1 zeros. So you just find these zeros and the poles, then you can determine g. this pose here, it is real part is, you see, this is in the middle here, should be 1, and the imaginary part is also 1, so this is 1 plus j. The other one is in the opposite location, there will be 1 minus j, so 1 plus j and 1 minus j. So we have pose 1 plus j and 1 minus j. And here is a 0. 0 is at location -2, right? -2. So the 0 is -2. Okay, then we know what is g. G is numerator is s minus 0, right? S minus -2. And the denominators, we have a minus, there's s minus the first pole and s minus second pole. So s minus this one, right, is this part, and s minus this one is this part. Then you need to do some calculation. I didn't give the process to find this result. That's your work, right? You need to do calculation. Yeah, you need to be careful because we have j here. The final result will be this. Okay. Yeah, it's some calculation about related with complex numbers. Yeah. So we have this one. This is g of s. All right. This is for the first part. And then the second part, we want to find the breakpoint. What is breakpoint? Actually, we need the whole transfer function, right? The transfer function of the closed loop system is this one. And then for the breakpoint, we need the denominator equal to 0, denominator equal to 0, as well as the derivative of the denominator is also 0. We need these two conditions. Then we rewrite this derivative as these, right? Derivative on s squared is 2s. K minus 2 times s is this one. Okay, so we have this equation. Then we try to solve it. So the process is like this. You find the m of s. This is coming from the gain formula, and plug in what is g of s to some simplify. You get this one. You get this one. And then let the denominator equal to 0. And the derivative of the denominator is also 0. Okay, so you have this part. Right? You have this part. Then we try to solve it. Okay, the second equation is quite simple. We can rewrite it as k equal to 2 minus 2s. Then plug in this k equal to 2 minus 2s in the first equation. Then we have s squared plus k minus 2, right? This is a k minus 2. This is k. 2 minus 2s is k. K minus 2. And here is a 2k. This is a k. Okay? And plus 2 equal to 0. Then we do some simplify. We have s squared and another s squared is here. Right? Negative 2s times s. Right? Another 2. Negative 2s squared. And these two numbers, they cancel. 2 minus 2. Right? They cancel. Okay, so they are zeros. And then I have 2 times 2 is 4. And 2 times negative 2s is negative 4s. And last term is 2. It's 2. It's a copy. Okay. So I get this one. Then I can combine the first two factors together, right? And this 4 and the 2 is also can be combined. Yeah, first two terms combined together. And this 4 and the 2 terms also combined together. So we have s squared, actually is a negative s squared. This is a negative s squared. Then minus 4s. I prefer the sign of s squared is positive. So I change the sign. This is a negative s squared, I write it as s squared. This is a negative 4s, I write it as a positive 4s. This is a 4 plus 2 is a positive 6. Positive 6, I put this in negative 6. Alright. Okay, so we have this one equal to 0. Then you can have this answer. You can just use the formula, right? It's a negative b plus or minus square root of b squared minus 40c over 2a, right? and it's the quadratic equation, the root of the quadratic equation. You have formula, you follow that formula, you can have this result. But you see, you have two results. It's -2 plus or minus. So which one do you want? You need to check the graph. You check the graph. Breakpoint is here, right? Breakpoint is here. So the result should be a negative value. Right? This side here is a negative something, right? This is 0. This is 0. This side is positive. This side is negative. So here should be -1. Then you can think it is a plus or minus square root of 10. Square root of 10, that will be 3 dot something, over 3, right? If here's 9, you get 3. This is 10, that will be 3 dot something. So if you use a plus, you will have a positive value. We only need a negative value, so we choose minus. So -2 minus square root 10, right, which is negative. Okay, we get this S. This is the location. This is just this location, right? Just this location. S is here. It should be a negative value. And then what is related to K? We know K is here. K is 2 minus 2S. So we plug in here. 2 minus 2S, and S is this one. Plug in, then we can have this value. Alright, so now we are done. And I write the conclusion here. We concluded that the breakpoint is this S, where the pole is where the K is this 6 plus 2 times square root of 10. So this is the one method. Okay. And we have second way. This method I introduced in the class and in the lecture. And the second way is given in the textbook. It is still use the denominator of this m of s, but in the first step, they choose the denominator, this part. Let this one equal to 0, and the derivative of this one equal to 0. Now, we're just working on this part, right? We use the derivative. We use this one. We take the we have the equation use this one equal to 0, and the derivative of this one equal to 0. And the second way is we start working here. We let this equal to 0 and derivative of this equal to 0. So we have these two equations. Okay, so what is the derivative? Now one take derivative is 0. You keep k, then g prime of s. So here should be k times g prime of s equal to 0. And we suppose k is a number larger than 0, so you just cancel it. You have this equation. Alright, then try to solve this equation. G is, let me make it, okay. Paper here. Okay. I put the bows. This one. Yeah. Okay. I have some space here. We want g prime s equal to 0, right? What is g? G is s plus 2 over something, right? Yeah, g is here. G is s plus 2 over s squared minus 2s plus 2. Yeah, this is g of s. This is g of s. So the derivative, the g prime of s will equal to, this is fraction, right? Fraction, so the derivative will be the denominator take a square, then the numerator take derivative on s, you get 1. So 1 times s squared minus 2s plus 2, right? So 1 times s squared minus 2s plus 2. And then minus, I keep s plus 2 and take derivative on the denominator part. So I have 2s plus minus 2, 2s minus 2. So I get this one. Yeah, it is this. It is this. It is this. Got it? Then do some. We want this equal to 0, so just numerator equal to 0, right? And the numerator, I keep these. Yeah, it's the same, right? And this one, if I times n, I have s plus 2 times 2s minus 2, which were equal to, like, times these, I get 2s squared, times these, I get minus 2s, and this is plus 4s, and this is minus 4. So it is 2s squared plus 2s minus 4. Right? I have this. And here's a subtract in front of it. So here will be minus 2s squared and minus 2s and plus 4. Alright. Then this one we get I combine this one, I have negative 2s squared, and this is 2s, there will be negative 4s, I change the sign here, and plus 2 plus 4 is plus 6, and here write as negative 6. You see? Same equation, right, with the first method, and the answer will be this one. Yeah, same as the method 1. Now, of course, if you work in the second method directly, from here to here, you need to use the formula to get it. Okay, after you get s, you want to find the k. You want to find k from this one. This one implies k is negative 1 over g. Negative 1 over g. And you plug in what is s. S will be, s is this one, right? And the g of s is that fraction, right? G of s here. So you replace s by negative 2 minus square root of 10, right? You have 3s term, s squared, and s. Replace all this s with this value, and then do some calculation, some simplify. Finally, you can have k. I don't work on it. I just show you the way. If you work on this, you should find this one. But you can see this method, you need a lot of more complex calculations. Yeah, the result should be this one. Okay. Now, of course, you can also use a calculator. You know what is s? Then you just use calculator, plug in, then you have result. But that result will be not like equal this with square root 10. It will be some, some real numbers, yeah, with like a 10 point something. This will be 6 to 12 something, 12 dot something, right? Okay, so this is the third problem. This is the third problem, right? Yeah, this is third problem. Now let's go to the last one. This one, we have a system and we have a Nyquist plot of this plot G. We want to determine K so that K can make the whole system to be stable. Okay, this is the problem. This is a feedback system, and we know what is G. We know what is G. Actually, I use the same G in the third problem, right? But here you will work on different problems. So even they are same problem, but they are not related, you can think. And this is a Nyquist plot, and using Nyquist stability criterion, estimate the range of K so that closed loop is stable. Okay, the solution I put in. So first of all, you should know what is Nyquist stability criteria. It is just this one, z equal to n plus p, where what is p? P are the poles of g in the right half plane. Okay, and this one you can look at the you look at here, right? You can know what are poles. Actually, we know the poles in the problem 3, right? In problem 3, it is 1 plus or minus j, right? 1 plus or minus j, right? We have this one. The poles are 1 plus or minus j. So you know we have 2 poles in the right half plane. So p is 2. P is 2. And then we need to determine n. And this n is related with k. What is n? N is a now we go over one by step by step. This one, depending on k, right? We have this graph. What is this graph? This graph is the Nyquist plot of k times g, right? You have g. You have the Nyquist plot of g. You have Nyquist plot of g, right? This is the g. Nyquist plot of g. And when you times k, it will be graph looks similar, but the scale is changing. Like if k is large, this graph will large. If this is small, it will be smaller. Okay. For example, k is 0.2, it will be just looks like this. And the k, if it's 10, it will 2. Okay, it will be like a double, right? Double, right? This is k equal to 2. This is k equal to 1, and the smaller one is like this one is k equal to 0.2, things like that. And you need to compare with this bar. You look at this bar and check how many times this Nyquist plot go across this bar. So you can see when k is small, the Nyquist plot is smaller, is close to the original point and will not touch this bar. So this case n is 0. And when k is smaller than 2, why is it smaller than 2? You look at the value of this point. You check it here. Check the graph. You see this point? This point, the value is negative 0.5. So when you times 2, this point will reach this negative 1. Here's a negative 1, right? But if you times k smaller than 2, it will, will not go across this 0. So in that case, when k is smaller than 2, this one, the intersection with this, they will be just there's a 0. Or maybe you think like you will have the case like this, the bar is here like this, but in this case you touch in this way and then touch in this direction, so they cancel. So go cross it and go back, so it cancel. Or even just no intersection, right? This one or this one. So this is the case n0. n0, this is 0, this is 2, you get z is 2. Okay, it's unstable. Why is it unstable? What is z? Z is number of zeros of the closed loop system on the right half plane. Now you have 2, so it's unstable. Okay, here's a k run from 0 to 2. Then when k is larger than 2, what will happen? Look at it. This is larger than 2, right? K larger than 2. K larger than 2, the curve will go across this bar, this straight line. So we have 1 intersection, 2 intersection, and the direction the curve is go across this bar from right to left. This is also from right to left. So I have two intersections, each with the same direction from right to left. Then n is -2. You got it? This is a anti-clock count, right? Anti-clock. The direction is anti-clock, so it's a -1. Here's another -1, so I have 2, -2, -2. Then you plug in here, P is 2, right? We know P is 2. P is 2. P is 2, N is -2, F, Z is 0. Okay, then the system is stable. The system is stable. Alright. Yeah. And then the third case, we go to the other direction. Now here's a K start from 0 to 2, and then from 2 to until infinite, right? This is a positive case. Then we check negative K. Negative K, first of all, because you times negative on this G of S, so the graph will flip like this way, right? Negative side go to positive side, and the positive side go to negative side. You will turn around this direction, you get this one. And then also, if the value is close to 0, no more than -1, for this case, the curve will look like this and do not have intersection with this line. This line starts from -1 to positive infinite, to some infinite, going up to infinite, right? No intersection. No intersection, that means n is 0. And n is 0, you plug in here, you get z is 2. Z is 2, so you have two poles. They are in the right half plane, two unstable poles. So the closed loop system is unstable. Then we K is from 0 to -1, then from -1 until -infinite. For this K, the cases look like this. Looks like this. And the intersection will be here, just one intersection. And the direction is from right to left. This is anti-clock, right? This is anti-clock. So this is also negative. The direction is n is -1. N is -1. N is -1. Plug in here, you get z is 1. That means you will have one pole in the right half plane. Right? The closed loop system, the overall system, has one pole in the right half plane. So the system is unstable. Alright. So now you discussed all the cases for different case. Right? K run from -infinite to -1, then to 0, then to 2, then from 2 to positive infinite. Then all the case you discussed. Then which part you have a stable system is here. Only this part, right? Only this part you get stable. All the other three cases, the system is unstable. So now we know when K larger than 2, the system is stable. Right? So we have our claim, our conclusion here. Then the range of K, so that the closed loop system is stable, is K larger than 2. K larger than 2. Alright. Okay, so this is the last problem. The fourth problem. Alright. Okay, if you have, I'm done. If you have any more questions about these problems, you can leave your problem in Piazza or discuss with me in my office hour or after or before the class. Actually, this Friday I will go back. I think if this is probability case, I think a 90% probability I will go back. Then I will give you announcement tomorrow after I visit the doctor. Okay, then that's all for today. See you next time. Bye bye.